point, right? This point has, I'm just taking one layer of this point, right? So imagine now that I have another layer slightly on top of this layer, on top of the screen, right? And then I have another layer still on top of the screen, and then I have a layer behind the screen that you see. So you can imagine a 3D object building up by this layer pattern, right? So that's, I generate essentially a three-dimensional structure, grid, right? A lattice, if you like, lattice of this black point. And these black points are in residual space. They are not real space. Okay, so first of all, that's key point to remember. So how do you generate this Ewald sphere, so-called Ewald sphere? So you pick one point. Let's say I pick this one to be my origin. Of course, you don't know where the origin is, right? Because if you're just talking about translation and symmetry, they should be all the same, different direction you see. But you can pick one point. Let's say pick this one. And then we put a vector from one point to another vector. Let's say go from here to 006. Let's call this one 006. And then from there, this becomes your radius. And from here, you imagine you start a balloon from this point, and you have a balloon, a sphere coming out with the radius of this vector. This becomes your radius of your balloon. And the balloon will intercept different points on your grid, on your lattice. Okay? Whenever you have intersection of the surface of your balloon to the grid lattice point, then you have a diffraction vector. Okay, so that's basically it. That's basically what I said here. So if you inflate your balloon, remember it's a three dimension, right? I'm just showing you a cut in the lattice. So in this plane, it intercepted 301, negative 301 point. Then you would expect to see a diffraction point here. Okay, you see one point in the diffraction corresponding to 305 point. Intercept 303 point, right? That's another point, and intercept this point as well. So you can see, but some point you're missing. You're missing this point. You're missing this point. You're missing this point and this point. So that immediately identifies which point, the spot you see. What are they, right? The spot you see on the diffraction pattern correspond to the intercepted point on your grid of this Ewald sphere when you inflate it. Okay? Now, if you change the wavelength of your X-ray, what is the effect? If you change the wavelength of the X-ray, you are basically changing the size of this radius. Okay, the size of the radius. So if you go slightly more and larger, then what you got is that you have a bigger or smaller balloon from that original point. And of course, if that happens, it will intercept different point, right? Different point that you got, right? And then you will see different X-ray pattern in the diffraction pattern. Yes?
So there it says like start at the origin, but the point there doesn't look like it's on any point of your lattice for that origin. It looks like a random location.
Yeah, so you can pick any point essentially, right? So I think you could pick on the origin, because of course you don't know how the beam actually coincide. Okay, so you can essentially pick any point in the space, and then you can work it out.
And it doesn't have to be a spot point.
No, it doesn't have to be a spot. Okay. And then you will use, because the diffraction is translatable, right, in free space. So, but what I'm trying to impress you is that when you change the wavelength, this balloon will intercept different points, and that's why you see different spots in your X-ray diffraction pattern. Okay, so it's quite a useful concept to locate, if you like, to locate diffraction spot, right, from this Ewald sphere that you have. So here we call it diffraction, and the reason why it works is the following, because if I have one spot here, right, one spot here, have another beam here, right, then these two spots, right, must be related to, right? If I have one spot here correspond to my incident vector, k pi, right, and the other spot is my if I have one spot here correspond to my k, incident beam, and then the other spot correspond to my k pi, because of the intercept on the spot, they must be related by some residual valence vector, because you can go from this point to this point by moving units of residual space vector to this point, right? Because this point is related to this point by some integral of big A and some integral of big B to get to this point. All right. So that's why it works. Is because if this is your incident vector, this is your outgoing vector, k and k prime, then they must relate on the Ewald sphere. They must relate by the residual valence. Okay, so now you can construct the same way for the surface neck that you got. So instead of 3-dimensional, instead of layer this grid that I try to get you to picture, you now have this is a little bit harder to picture in some way. You now have just a layer. Okay, I'm trying to draw it in 3-dimensional perspective. So the red point here is my residual neck point that I got. Okay. Now to generate the Ewald sphere in the same way, imagine that these residual neck point are spotlight, and you turn on the spotlight, and there are beam of light going through, and this is called these are rod structures sticking out from the center. And now you pick any point on here, and again generate a Ewald sphere. So again you have a balloon, and wherever you cross this, wherever you call the spotlight, right, then you would have the diffraction condition. Okay, it's a little bit hard to so everybody follow me. So you have again, if you have, these are my so this is my 2-dimensional grid. They have a rod coming out from the surface, right? These are residual space point, and I'm going to cut a plane across one of this set of points that I have, and I redraw it like this. Redraw it over here, and you will see all this little line. This line correspond to my rod that's sticking out. So you will see all this line sticking out correspond to each of these points. And now I set up a vector, let's say from here to here, right? And again construct a Ewald sphere, meaning that I have a balloon in the middle, and then I blow up this balloon, and you see that it crosses all this rod. And wherever it crosses the rod, that will be a diffraction condition. It will satisfy the diffraction condition. Okay? And you will see that it's a little bit trickier, because if you change the energy, right, what does it mean? When you change the energy, you change the size of the balloon, in fact, because the magnitude of the radius, right, which is k, you change the magnitude of the radius. So you're basically inflating more of this. And what is the effect? You will see the spot actually move, right? Because here I see all this little diffraction intercept that I see. If I change the energy, I see the spot moving like this. Okay. So when I change the kinetic energy of the beam, I will see some spot moving in, some spot will disappear, some spot will reappear on my lead optics, because my diffraction condition changes on different residual space points. Okay. So here I point